Welcome everyone to another video. In this video, we're going to find the internal resistance and EMF of the circuit shown in this diagram. Now, if you'd like a recap of what internal resistance is and maybe how to deal with a more basic example, feel free to watch my previous video that dealt with an internal resistance problem that only had one other resistor in series. This problem will be a slightly more complicated one as it incorporates parallel and series relationships within the same problem. Now, one of the fundamentals of this particular circuit diagram is noticing two things. One, there's a switch as indicated by the blue in this diagram, and two, there's an ammeter. Now, an ammeter is a device that measures current flow in a certain area of the circuit. As we go through this problem, you'll begin to see that the placement of both the switch and the ammeter is vital in order to start understanding how different currents are calculated within this circuit. The two pieces of information we're given about the circuit is that when open, this ammeter records a value of 1.3 amps, and when closed, it records a smaller value of 1.25 amps. Now, what's the reason for this difference? Well, this is where we have to look at switch placement. When the switch is open, it essentially breaks the path that leads to the 6 ohm resistor. Thus, when the circuit has an open switch, only the 3 ohm resistor has current flowing towards it. This is what the circuit looks like when the switch is open. Only the 3 ohm resistor and the little r resistor are still important to understanding the circuit. Now we're given that the ammeter records a current value of 1.3 amps in the open configuration. That means that 1.3 amps goes through the 3 ohm resistor. Now, eventually we want to find out what the EMF and little r values are in the circuit. How do we start to figure that out? Well, according to Kirchhoff's loop law, we can calculate EMF values by remembering that any complete closed loop around a circuit has a total potential difference of 0. That means when you add up all the delta V's in a circuit, it should amount to 0. Specifically in this case, our EMF minus the voltage drop across our little r resistor minus the voltage drop across our 3 ohm resistor, that should all end up equaling 0. As we look at this equation, we should think about, is little r's current the same as the current flowing through big R? Yes, because little r and the 3 ohm resistor are both in series with each other. Since they're in series, they have the same current flowing through them, but their potential difference drops are different. All right, so let's look back at Kirchhoff's loop law. The things that we know and can plug into this equation are our big R value, that's 3 ohms, and we know that all the current values are the same, they're 1.3 amps. So rearranging and combining terms from the loop law, we then can get an expression in terms of EMF and little r as shown here. Now, we have two unknowns still in this one equation, so we need another equation in order to be able to solve for those two variables. That's when now we consider the closed loop configuration. As a reminder, this is what our original circuit looked like. So now if we close that switch, we have a complete path that also leads to a 6 ohm resistor. As such, this is what our closed loop looks like. In order to begin to understand the relationships within this new resistor, let's think about something. Parallel resistors have the same value of what variable? Do they have the same current? No, that's true of series resistors. What about potential difference? Yes, they do have the same voltage drop across them. This is a good relationship to now use. Since we know that the delta V across a 3 ohm resistor is equal to the delta V of this across a 6 ohm resistor, we can now manipulate this by remembering Ohm's law, which is V is equal to IR. Substituting those appropriate variables into this equation, we realize that we know what the current across a 3 ohm resistor is. That's one of our givens. It was 1.25 amps. Therefore, we can solve for the only remaining variable, which is the current across a 6 ohm resistor. And through a little math, we get that it's 0.625 amps. Again, remember to keep the big picture goal in mind. We eventually want to find the EMF and the little resistance R. In order to find EMF, let's think. EMF is essentially the equivalent voltage or total voltage of the circuit. Well, to get equivalent voltage, we need the equivalent current and the equivalent resistance. So how do we get equivalent current, especially in such an example as the closed configuration? Let's bring in another one of Kirchhoff's rules, specifically Kirchhoff's junction rule, which states that the total I going into a junction should equal the total I going out. What does that mean? Well, let's look at the diagram. Here's the positive end of our battery as indicated by the longer line. Our current starts to flow this way into the circuit. Now, the current has a total value here. So let's call this I1 as an I initial. But then because of this junction, it splits off, leading through an I that goes to the 3 ohm resistor and an I that goes into the 6 ohm resistor. Let's write this out in terms of an equation. The I equivalent is equal to the current going through the 3 ohm resistor plus the current going through the 6 ohm resistor. We just found both of those values up here. Plugging in those numbers, we get an equivalent current of 1.875 amps. Let's use this value to now find our total voltage, or EMF. EMF, once again, using Ohm's law. We're multiplying these two values, current and resistance. We just found current. What about equivalent resistance? Well, what kind of relationship does 3 and 6 ohm resistors have? They're in parallel. That combined resistor is then in series with our little r, which is very similar to what we just saw in the open configuration of the circuit. In order to combine these, we take the reciprocal of the 3 and 6, add those and take the reciprocal again to get 2 ohms as the combined resistor of 3 and 6. Then we simply just add that mega resistor to our little resistor because those again are in series. Plugging in this new expression we got for REQ, we're left with this. Another equation left in terms of EMF and little r. Well, that's the same thing that we got, or very similar to what we got as our final answer for the open circuit. We have two equations now, both in terms of EMF and little r. Two equations, two unknowns. That means we're ready to solve. All that's left now is plugging in those two equations. So both of them are in terms of EMF, so set them equal to each other. After a couple of algebra steps, not too painful, right guys? We eventually can end up isolating little r and getting a value. Once we have that, we can then plug this value of little r back into either of those two equations to get an EMF value. And that's it, guys. Those are our values for little r and EMF. One last thing that might be helpful is to assess your answer. What I mean by that is to see whether your answer is reasonable, considering the context of the problem and the values you then got. The internal resistor of the battery, we expect from the very beginning to have it be a lot smaller than the other resistors in the circuit. And this is what we got. our resistor is only 0.26 ohms, whereas the other resistors in the circuit are 3 and 6. So they're all within the same ballpark, but it's clear that little r is much, much smaller than the other r's. Another thing is that we got a reasonable answer for the voltage of our battery. 4.24 volts is perfectly reasonable for a battery, especially considering the current values that we got. So we can be rest assured that we did our math correctly, we applied our physics correctly, and that this answer we can be confident in. If you have any follow-up questions, feel free to let me know in the comments, as well as if you have any suggestions for other videos or topics you may be struggling with. Please like this video and subscribe to this channel if you'd like to see more content like this. And good luck, guys.